For the next 2 hours, we have 4 presentations to explain the past and future capabilities of MSP platforms, coding technologies, and the measurements that can be performed as part of an MSP expedition. Okay, so I'm up first. I'm opening today's series of primer talks with an overview of the capabilities of mission-specific platforms, or MSPs, and coding technologies, and I hope to do so in a way that will be of specific interest to anyone thinking about developing an IODP MSP proposal. Although my colleagues and I have given many presentations conveying the MSP concept in general, we felt it would be useful to present something that is more tailored for potential MSP proponents to better inform you of what the general capabilities of MSPs are and where the existing MSP concept could be adapted to better meet the requirements of your proposals. So to get started, I know many of you are probably familiar with the structure of IODP and the role of MSPs, but in case there are any newcomers today, and you're particularly welcome if you are a newcomer, I'd like to offer a brief introduction to MSPs. First, I will quickly explain who ESO are, ECORD Science Operator. We're a partnership of 4 institutes, the first being my institute, the British Geological Survey, and I'm based in their Edinburgh office in the UK. The BGS ESO team are responsible for coordinating the ESO partnership and for designing and building and managing the offshore operations. So we're basically responsible for sourcing the vessels and the coring technologies. The second partner institute is the MARUM, the Centre for Marine Environmental Sciences at the University of Bremen in Germany. And the Bremen ESO team are responsible for the core curation, the provision of offshore and onshore lab facilities, and the databasing. And we'll hear from my MARUM colleague, Patricia Gebregs, later on about the MSP scientific measurements. The third entity is the European Petrophysics Consortium, or the EPC, comprising 2 institutes, which are the University of Leicester and the University of Montpellier. And the ESO EPC team provide core physical properties and downhole logging services. And we will also hear from them later via my colleagues, Katrina Hochmuth and Erwan Lebert. So together, the 3 partners of ESO work with various subcontractors and other contributors to implement MSP expeditions. And we do that on behalf of ECORD under the auspices of IODP. So IODP relies on various drilling platforms to deliver its science plan, with those platforms provided by 3 funding consortia led by the USA, Japan, and ECORD. And each consortium has an appointed operator. The USA and its associate members provide the JOIDES Resolution, or the JR, a riserless drilling vessel and the workhorse of the programme for the last 35 years, and operated by our colleagues at the JOIDES Resolution Science Operator. Japan supplies the Chikyu, IODP's huge riser drilling vessel, capable of very deep drilling, potentially up to 10 kilometers below the sea surface. And the Chikyu is operated by JAMSTEC in Japan. Now, both of these vessels are extremely capable for scientific drilling, but they can't work everywhere where we want to do geoscience. And this is where ECORD steps in through its operator ESO, i.e. us. And we work to contract vessels and coring rigs and put together the scientific facilities needed to conduct IODP-style missions on any suitable vessel. So why are MSPs needed? Simply put, they are needed to complement the JR and the Chikyu to allow IODP to reach a greater range of scientific targets. And there are 4 main barriers that MSPs help to overcome. The first is to be able to work in shallow water, less than 90 meters. So 90 meters is pretty much the minimum water depth that the JR and the Chikyu can operate in, although I do understand that there is a little flexibility in that number. So IODP needs the means to access water depths that are shallower. So why 90 meters? This is the clearance of pipe needed between the JR or the Chikyu and the seabed to allow enough pipe flexibility to stay within the capabilities of their dynamic positioning systems. And 5 of the 8 MSP expeditions that we have completed have had sites in less than 45 meters. The second is to be able to work in ice-infested waters. So in polar regions where it is basically not safe for either the JR or the Chikyu to work in such conditions as they have no ice rating. We've completed 1 MSP Arctic expedition in heavy ice in 2004, and we are currently planning for a second Arctic expedition. The third type of barrier is other physical obstacles, a good example being low bridges, which can block some taller drilling derricks from passing underneath. And we've had 2 expeditions where this type of barrier had to be overcome. And the fourth is to work in lithologies where alternative coring methods might yield better recovery. Now, broadly speaking, MSPs are made up of 4 basic elements. The first element is the platform, which is a vessel of some kind. The second element is the coring method, which is occasionally permanently integrated into the platform, but in most cases it is separate, which is why I will be dealing with them separately for this presentation. The limits of MSP capability are generally determined by one or both of these basic elements. And as you will see later, the minimum water depth tends to be controlled by the platform, while the maximum water depth tends to be controlled by the coring technology. And it is also the coring technology which controls the maximum penetration. So more on that later. Although we can view the platform and the coring method as separate in most cases, so essentially taking a pick and mix approach, we will see later that certain types of vessels are naturally suited for deploying certain coring technologies. The third element is the offshore analytical facilities, which we usually temporarily install onto the platform using a series of containerized labs. And the final element is the onshore analytical facilities, which are based at the Marum and the Bremen Cove repository in Germany. This onshore facility is needed as we can't carry out the full suite of measurements on our vessels of opportunity due to space issues, and therefore we don't split the cores at sea. So I'll not cover these last 2 elements, elements 3 and 4 in detail, as they will be covered by my colleagues speaking next. But the only thing I will highlight at this time is the fact that there is a time gap between the offshore and the onshore phases, which lasts from a couple to a few months. And this is the time when we transport the whole cores to Bremen and we store them there ready for the onshore science party. But in recent years, we've worked with the science party to make more use of this time for additional measurements, and I will leave it to my colleagues later to describe those additional measurements and to explain how this time period represents an opportunity for new measurements on whole cores to be introduced to IODP. So I'll base the rest of my talk on the first 2 elements, the platform and the coring method, and I will share ESO's experience and knowledge of the various platform options that are available. Okay, platforms. So when thinking about MSP platforms and coring methods and how effective they might be in delivering your science, there are 2 basic approaches you can take. The first approach is to look back at past MSPs and use them as proven templates. So for these expeditions, we know the ships, we know the coring rigs used on them, we know the coring rates and the recoveries that we achieved. We know the deck layout and the core flow and what worked well and maybe what didn't work so well. The second approach, which is more challenging, is to think about platforms and coring technologies that haven't been used in IODP MSP expeditions before. So to date, we have completed 8 MSP expeditions with a 9th in planning, using 9 different platforms, and these can be loosely grouped into 3 categories. The first group are dynamically positioned geotechnical vessels, multi-purpose vessels, and converted supply vessels. So these vessels tend to host heave-compensated geotechnical rigs that are quite a bit smaller than the rig on the JR, and the rigs also tend to be temporarily installed on the vessels. The second grouping are the liftboats or other self-elevating platforms, and their unique characteristic is that they are self-elevating standing platforms, and they look very much like miniature oil rigs, and they are self-propelled, highly versatile, and like most MSPs also require temporary rigs to be installed on them. And in the third category are scientific research vessels, which are obviously suited to deploying alternative coring methods such as seafloor drills and giant piston coring. Now, when I use the phrase alternative coring methods, I use it to mean any coring method that isn't rig-based wireline coring. So as you can see from this table, the sizes and types of vessels that we have used are quite varied. The largest vessels we have ever used are still only about 2/3 the size of the JR and only around half the size of the Chikyu. Of the 9 vessels that we have used, only one, the Fugro Synergy, on Expedition 381, Gulf of Corinth, only that vessel has had a permanent integrated rig. All the rest had temporary rig setups, which is itself challenging because even if the individual MSP elements have been tried and tested, the whole setup has never been tested until the expedition happens. And there is often a steep learning curve for everyone involved, the contractor, ESO, and the science party. There's a learning curve before we understand the true capability of any particular MSP setup. Okay, to simplify things, we can look at the general capabilities of the three vessel categories as used in MSPs. So taking geotechnical and multi-purpose vessels first, we can see that although we have used this type of vessel in water depths between 23 and 1288 meters, they can in fact operate in as little as 10 meters water depth. So as I explained before, when drilling, the minimum water depth is dependent on the capability of the dynamic positioning system. So you can imagine that a short distance of pipe between the ship and the seafloor has much less tolerance for movement, and so the ship must be more strictly held in position to avoid bending and possibly breaking the pipe. So although the very shallowest that these ships like these can operate in is around 10 meters, it's questionable that the vessel or perhaps the drilling company would be comfortable coring in that water depth, as being successful also depends on other factors, including tides and currents and swell and weather. So I would personally put a rough limit of 20 meters on the minimum water depth for platforms such as these. In terms of maximum depth, well, this is limited by the coring technology, which we will come to later. Other advantages of these vessels are that they are easily movable between sites. There is no need for a seabed survey to land any legs and elevate. There is generally good market availability. So despite a shrinking market and takeovers of smaller companies, there are still competing options out there that we can access. Also, these vessels can basically transit to and from anywhere. So as long as ECORD is willing to pay or part pay the transit costs, these vessels are more or less globally ranging. Disadvantages are that these types of vessels can be affected by swell, so we must rely on effective heave compensation for the installed coring systems. And even the best systems still convey some movement to the bottom hole assembly at the base of the borehole, and that can affect core recovery. And finally, these vessels being in constant dynamic positioning, it takes extra fuel, which has a cost implication. And they can be noisy, which can be fatiguing for people working on board. Moving on to lift boats, these have been proven to be highly successful MSPs, and we have used platforms like this twice on New Jersey and Chicxulub. Now, these vessels can access very shallow water, and although the very shallowest that we've operated in is just under 20 meters, it could be as little as 4 meters, taking the example of the lift boat Cade that you see in the top picture there. These platforms are attractive for scientific drilling because they essentially offer a land-based setup. So when these vessels are elevated, there is no swell, and we can use land-based mining style coring technology, which, as I will describe later, brings many benefits for coring. They're comparatively quiet platforms, they're less fatiguing, and they burn less fuel. So lift boats, they have a lot going for them, but there are a few drawbacks. The first is that they only operate in a narrow water depth range, so from a minimum of 4 meters up to a maximum of 110 meters for the largest lift boats. So for this type of platform, the maximum water depth is in fact controlled by the vessel, not by the coring technology. Larger lift boats will increase the costs, and if you need to go above 110 meters water depth, the next size of platform up is the jackup rig, and they can operate in up to 150 meters water depth, but these are very much more like small oil rigs, and they start to become prohibitively expensive. As you may remember from my previous summary table, lift boats are the smallest platform we have used, so they generally have less accommodation space, so there is a greater chance of having to share cabins, and we use 6-person cabins offshore New Jersey. These elevating platforms require seabed site surveys, basically geophysics and cone penetrometer tests, and that's to ensure that the ground conditions are suitable for prolonged occupation, so that extra survey requirement adds extra logistics and costs. And the final point on lift boats is that these vessels cannot easily cross oceans. They are generally only available near market areas. And the reason for this should be obvious from this 2009 image of us leaving Atlantic City on the Liftboat Cade on the New Jersey expedition. And you can see that these lift boats are rather strange looking things that sit low and flat on the water, and they're just not suitable for rough seas. They move around on shelf areas within their depth limits, and should any bad weather or sea conditions arrive, they simply elevate and wait it out. So for the Chicxulub expedition, we mobilized in Louisiana, and we had to transit around the Gulf of Mexico to stay within the vessel permitted water depth. And that transit was basically 3 times further than the direct distance. So you can imagine that getting a lift boat to, say, a remote island location would be challenging, and would probably need to use a large ship transport and large craneage, and I would imagine that would be prohibitively expensive. So these lift boats are best for expeditions in certain locations near lift boat markets and with sites that are in a narrow water depth range. If the site water depth range has to be wider than the capabilities of a lift boat, then you need to move to a geotechnical vessel. The final MSP platform is the scientific research vessel, which we've used once for Expedition 357 Atlantis Massif. We used the James Cook, and we are planning to use the Japanese research vessel Kaimei for Expedition 386 Japan Trench. These vessels are the natural choice for smaller scale coring technologies such as seafloor drills and giant piston coring. So these platforms offer a cost-effective way to deploy smaller scale coring methods. They tend to have sizable, well-equipped labs, and so they offer a place where third-party measurements and equipment can be integrated with an IDP expedition. The vessels tend to be nationally owned assets, so they offer in-kind contribution opportunities for countries whose research community has particular interest in a certain proposal. If an in-kind contribution can be realised, then the country making the contribution is rewarded with greater science participation for its researchers. And also, this also means that it's less cost to ECORD, which is obviously attractive when the ECORD Facility Board considers scheduling options. And as far as I can see, there are no major disadvantages of using scientific research vessels in IDP, other than perhaps they can only carry the smaller scale coring equipment. Okay, so that brings us to a point where I have covered the platforms that we have previously used as MSPs. But before I move on to discuss the coring methods, I'd just like to look at some possible future vessels that may open new areas for MSPs. So the first vessel that we should look at is a modular platform, such as this example manufactured by CombiFloat. So this platform can operate in moored floating mode, so a bit like a moored barge, similar to what ICDP uses in lakes, or it can be used in floating mode with dynamic positioning if the sea conditions allow. These platforms can also elevate, and this particular CombiFloat platform with the extended leg option can operate in water depths of up to 56 meters. The platform size can be altered, so not all the container blocks need to be used. And crucially, it can be transported and mobilized almost anywhere. So the whole system is shipped in pieces and does not have the same transport restrictions that a lift boat has, for example. This platform also has decent deck space. It actually has more deck space than either of the lift boats that we've used for New Jersey or Chicxulub, due to there being no major infrastructure other than a small control house. However, there's no accommodation on this vessel, so either you need to have an onshore base nearby if the sites are close enough to the shore for a commute daily, and failing that, then you need some temporary accommodation to be installed on board. So this is an intriguing platform that was brought to my attention only recently because the Continental Scientific Drilling Coordination Office in the US is putting together a proposal to NSF to acquire this platform. And that's to support various projects, including ICDP projects and potentially also MSP expeditions. So they reached out to us to explore the possibilities of using a vessel like this on MSPs. And I think there certainly could be possibilities in the future. So I promised to highlight this vessel to you today. I think the proposal doesn't go into NSF until September, and it will be sometime after that when the Continental Scientific Drilling Coordination Office learns if they've been successful or not. Other potential future platforms that are almost ready are 2 icebreaking research vessels, which are catching our attention. These are the RSV Nuina you see at the top there, which should be delivered to the Australian Antarctic Division later this year. And of course, the Sir David Attenborough, which was recently launched and will soon take up operations for NERC and the British Antarctic Survey. Both these vessels provide opportunities to use alternative coring methods, such as seafloor drills around Antarctica. And we've been exploring possibilities with both the AED and BAS to use these vessels as MSPs. And later on today, we will hear from Rob Larter about the SDA and its MSP potential. So up until now, I've mainly focused on the platforms. I'd like to talk more now about the coring methods. So this slide will shortly summarize all of the coring technologies that we've ever used in MSPs, and I've categorized them into 3 basic types. So the first category is offshore wireline, and I think people will be most familiar with this type of coring as it's been the bread and butter of scientific ocean drilling for decades, and it's featured in 5 out of our 8 MSP expeditions. So this type of coring is done from heave compensated rigs, where the torque is applied to the drill string at the rig, and the core barrels and other drilling tools are swapped in and out of the bottom hole assembly by means of a wire. The second type of coring used so far in MSPs I have called mining style wireline. So this is quite similar to offshore wireline, except there is no heave compensation. These systems were designed for mining related drilling on land, and therefore you need a stable platform. So these mining systems are generally much smaller and lighter than the rigs and the drill pipe needed for offshore wireline coring. The drill pipe is thinner and lighter. The coring bits are narrower, but the same diameter of core can be recovered. And also, since the whole system is lighter, it is also nimbler and more responsive, and the core quality can therefore be very good in formations that offshore wireline coring sometimes struggles to core, such as the loose sand intervals that we cored during the New Jersey drilling. The third grouping is the alternative coring technologies. So that's basically seafloor drills, gravity coring, and giant piston coring. And we have used or are planning to use all 3 of these methods on MSP expeditions. Okay, so let's look at some figures from past MSP coring methods. So I will summarize these figures shortly in terms of the general coring method categories, but I wanted to show you this table as it illustrates our experience of some of the key coring variables on different expeditions. So this table lists the 9 main coring rigs that we have used in MSPs. And the first thing to note in column 2 here in yellow is that we have never used the same coring rig twice. So it becomes fairly difficult to make comparisons between the various coring rigs, as we can't separate out performance related to the technology and performance related to the geology. Column 3 describes the coring tools that were used in each expedition. So again, we have used a variety of coring tools, and they almost all share the same basic coring principle, which is that they latch into the bottom hole assembly, be it deployed from a heave compensated rig or a mining style rig or a seafloor drill. So although the coring tools are variable, the core diameters they recover are generally similar. So we're looking at typically between 61 and 63 millimeters diameter, although we did recover a slightly wider diameter core of 83 millimeters during the Chicxulub expedition. And obviously giant piston coring does offer a much wider core diameter of 100 millimeters. In terms of drill pipe length deployed in MSPs, shown in column 4, this has varied widely from over 1.7 kilometers on expedition 302 to just over 16 meters from a seafloor drill on expedition 357. And this penetration range reflects the variety of coring technologies that we have used. However, in all cases, we didn't fully utilize the maximum drill string deployable by the coring system. So this is shown in column 5, which I think will be of more interest to the proponents. So the maximum drill string deployment is controlled by the strength and the capacity of the rig, which in turn controls the maximum penetration that can be achieved. And you can see that there is a variation in the maximum drill string length, but I want to come back to these figures in a summary table later. Similarly, the average coring rate and the core recovery shown in the last two columns, they're highly variable in MSPs, and these are the hardest variables to offer estimates before an expedition for obvious reasons. Something that is consistent is that the general MSP coring rate is much lower than that compared to JR expeditions. So in the JR, coring rates can easily exceed 100 meters per day. But again, I'll come back to the coring rates when I summarize in a moment. But just before I summarize the coring methods, I'd like to first talk about seafloor drills. So seafloor drills are a coring technology that I think still need time to shine for IODP, but I do believe that they hold huge potential. So I've counted 14 systems that are either in service or will soon be in service, and you can see them all here on the slide. What I can't say for certain is if all these systems are potentially available to IODP. So most of these systems are commercial and they're mostly used for site investigation work. But we have spoken with some suppliers of these systems and they are willing to consider ESO as a future client. However, I wanted to highlight these drills to demonstrate their general capabilities. So this slide illustrates the general size of these rigs. So some rigs like the BGS Rock Drill 2, they're quite compact and they can fit through, and they can fit through moon pools, but others can be a lot bigger than you think. And that's important because to use these seafloor drills on research vessels, the vessels need to have the correct deployment equipment and A-frames that are large enough to carry the drills. And also many of these drills are just simply too big to fit through a moon pool, and therefore they need to be deployed either over the stern or over the side. So the concept of these drills is relatively simple. These are mobile drills lowered to the seabed using an umbilical that carries the power and the communication and the control. And then the drill pipe and the core barrels and other tools, they're manipulated to and from a carousel or magazine using robotics. And then an onboard top drive provides the rotation for the coring, and an onboard mast feeds the drill pipe into the seabed. So here's a summary table of the 14 seafloor drills that appear to be or will shortly be in service. A noticeable feature of these drills is their limited penetration compared to surface-based drilling. So their penetrations are varied, but they generally range between 50 meters and 150 meters, with one exception being the MEBO 200, which can reach 200 meters below seafloor, although it can only do that not by coring continuously. It can't do that by continuously coring from seabed in one hole. We can also see that the core diameters are mostly at least as wide as that standard IODP core diameter at around 61 to 63 millimeters. And in many cases, it can actually be larger, up to around 72 or 73 millimeters. And in the case of the Royal IHC Sword, it can be up as high as 102 millimeters, so basically as wide as a giant piston core. And finally, the water depths for these drills, they're limited either by the rating of the equipment on board or by the length of the umbilical. And the depths are generally between 2 and 4 kilometers, with only the older Williamson system here at the bottom able to reach 6 kilometers water depth, albeit with narrower core and shallower penetration. So to summarize these coring methods, I'd like to provide some general rules of thumb that proponents might find useful when thinking about implementation. Taking offshore wireline first, so the core diameter is typically between 61 and 64 millimeters. The maximum coring depth for this method on MSPs is generally between 2 and 3 kilometers. And the coring rate is, it's hard to estimate for MSPs, but I would suggest using 50 meters per day as a reasonable starting point. So offshore wireline coring is a tried and tested coring method. It has an excellent recovery track record across many platforms going back decades. These rigs are generally available from various market regions across the world. As I've mentioned, they offer deep penetration. So on MSPs, generally up to 3 kilometers. Theoretically, other vessels and rigs that can go deeper could be sourced, but I think those would be prohibitively expensive under normal market conditions. This coring method offers the fastest MSP coring rate, and these rigs also offer many possibilities for downhole logging and borehole instrumentation, because you can access the borehole from the platform and you can push and pull equipment downhole as you need to. A disadvantage compared to the other systems is that the platform and the supporting infrastructure can be costly, as I said, especially for larger rigs that are needed for deeper penetration. Looking now at mining style wireline coring. So the core diameter is between 61 and 83 millimeters. The penetration depth is also reasonable, up to 2.4 kilometers. And in our experience, the coring rate is slightly less than offshore wireline coring at around 30 meters per day. Like offshore wireline coring, these are proven coring systems. They are generally available, and due to their smaller size, they're much more easily transportable around the world. The penetration is good for MSPs, as I've said, and like offshore wireline, you have that borehole access to run and install other tools and equipment downhole. As I explained earlier, the entire system is lighter, so that offers several benefits for core recovery. But to gain these advantages, you need a stable platform. So that's most likely an elevated platform, but also potentially a moored platform in calm waters. So you can actually use these systems if you have excellent heave compensation, but your penetration will be limited in such a setup, probably to maybe just a few hundred meters due to the weaker pipe that's being used. And that weaker pipe has to handle more movement under a heave compensated scenario. Moving on to seafloor drills, the core diameter with these systems is more variable, between 44 and 102 millimeters. And the penetration depth is a lot less, generally between 50 and 200 meters. And the coring rate is the slowest of all the MSP coring methods. So you're looking at around 15 meters per day, although it does vary quite widely between the different systems, but typically it's around 15 meters per day. So these drills can be cost effective when combined with a research vessel in-kind contribution. They can operate in parallel to other coring systems on the same expedition. They're particularly suitable for investigating shallow horizontal variability. And being on the seafloor, they experience no drill string heave, so you can achieve better core quality in certain lithologies and at certain depths. Like mining systems, the seafloor drill systems are lighter and they can offer better core quality. The wider core diameter is available with some systems, however, they do have limited penetration. And the track record of seafloor drills is not as mature as other coring methods, but it is building. And finally, downhole logging and instrumentation on these systems is limited, and it is only available with certain drills. So to expand that point, it is really only the two academic seafloor drills, so the Rock Drill 2 and the MEBO drills, that have additional logging and instrumentation of the type that is of most interest to scientific ocean drilling. The commercial systems do carry additional tools, but they tend to be geared towards site investigation. So in preparation for Expedition 357, ECORD invested in developing extra capability for seafloor drills, and both the Rock Drill 2 and the MEBO drills now have some downhole logging memory tools, but obviously not the full suite of tools that you might expect to run on a normal IODP expedition. The two drills also have a tracer injection system to assist with assessing core contamination for microbiology work. Both drills are able to deploy simple borehole plugs to seal off any circulating fluids for later sampling. And also both drills can carry ancillary equipment, such as water collection and borehole fluid chemistry sensors, and those are to collect additional in situ data to complement the core and the log data. Okay, finally, let's look at giant piston coring, which is our final coring method. So like seafloor drills, giant piston coring can be very cost effective when combined with a research vessel in-kind contribution. Like seafloor drills, they can also operate in parallel to other coring systems. They're particularly good for investigating shallow horizontal variability, but their unique strength is their suitability for ultra deep water. So for example, the deepest water site for our Japan trench expedition is just over 8 kilometers water depth. The system does offer a wider core diameter of 100 millimeters, so you get more material to play with, despite the shallower penetration. And also giant piston coring has a good track record, but the penetration is limited and there is no downhole logging. Okay, good. So in a moment, my colleagues will take over the story to talk about scientific facilities and measurements. And later we'll hear more about the Sir David Attenborough as a possible MSP. But just to finish off my part, I'd like to offer a few takeaway messages. So first, when constructing a proposal, I would recommend always putting the science first. So we do not want operational matters to discourage new and adventurous ideas, and your scientific ideas, they need to stand up to scrutiny. So that should really be your main focus. There are plenty of opportunities for reality checks after the original idea is formulated. So IDP proposals, they go through a kind of iterative process, and there are people in the IDP system that are there to assist you to settle on an appropriate final version of your proposal. So implementation is really a secondary concern for proponents, but however, having said that, it is still a very important aspect that proponents should try to consider as early as possible and to try and develop an awareness of feasibility. So how to do this? Contact an IDP operator before submission. So invite them to your workshops. As a minimum, email them. And this is especially true for MSP proposals. If your proposal is an MSP proposal, try to keep your scientific targets within the platform and the coding capabilities that I've outlined today. And if you don't do that, then you're basically challenging ESO to find new and possibly expensive ways to implement your proposal. And maybe that's just the way it has to be, and if your science is inspiring enough and strong enough, maybe ECORD will invest more resources to make it happen. But if you follow a blue skies approach to implementation, it is arguable that the chances of eventually getting scheduled will fall away. So, please ask yourself, can my objectives be met with fewer and/or shallower boreholes? Another thing to ask is additional sampling or analysis needed in addition to the primary coring and IDP standard measurements? So these are questions you could have in mind when listening to the next talks about measurements. Finally, is a vessel in-kind contribution a possibility for your proposal? So if it is, can you include details of any ship time inquiries or any agreements that you might have made in your proposal? This would make a proposal much more attractive to ECORD to have those details included at an early stage. Okay, I'll leave it there. Thank you very much for listening. I hope you found what I've presented interesting and useful for thinking about new MSP proposals. We have a few minutes in the schedule now for questions, so I will leave my slides up in case I need to refer back to any of them. And I believe now Jude Coggan will step up to chair the Q&A session.
Thanks, Dave. So if you have any questions, please just type them into the chat on the side there, and I'll read them out in turn as they come in. So we have a question from Gilbert. To start you off, Dave, please can you let us know what would be the steepest slopes on which the combi float could operate?
Yeah, that's a great question, Gilbert, and it's one that I don't have the answer to at this moment, but I will seek to get the answer as fast as I can. I can get in touch with CombiFloat or with the guys in the US who are looking to acquire it and get that answer. That is a good question because it is key, I can imagine, for a lot of proposals.
Thanks, Dave. Okay, we have a question from Becky Hopkins. Typically, when a different drill rig is installed on a vessel, do staff from the company generally join the ship party?
Yeah, so when we have a separate rig, so you'll have the ship's crew, so they'll be on the vessel, but then you also need the drilling crew as well to operate the rig. So they will join the expedition as a contractor, but they won't be part of the science party. So they don't generally join in with the science. Many of them do show an interest and they like to do the best job they can for the scientists, but they won't formally have a scientific role, but they are on board helping with the offshore team.
And so presumably you have to take that into account when you're thinking about the amount of accommodation on board and things like that.
Yes, yeah, and that's one of the hardest juggling acts that we tend to do on MSPs is, how much room is left over for scientists and ESO staff after you take into account all the subcontractors. And some of these larger rigs, they do take a lot of people, and if you're operating 24 hours a day, you need to have 2, possibly 3 shifts, and yeah, it does take up quite a bit of berth space, so it is something that we have to be careful of.
So on a perhaps you could talk about the range of the size of science parties you've had on previous expeditions.
Yeah, that's a good question. So typically, so a science party in total is usually around 30 people. It can vary between maybe 28 and 32 people, but it's about 30 people. And all those people would join the expedition and come to Bremen for the onshore for the onshore part. Only a subset of the science party will actually sail offshore. So the number of people sailing offshore would vary, maybe typically between 8 and 12. So you're looking at maybe a third of the science party would actually get to sail offshore. Depending on the size of the vessel and the number of berths, you could potentially increase that number, but you have to be careful that you have jobs to do or roles for those people offshore. Remember, we don't split the cores offshore, and if you have too many scientists offshore, then you might have people basically twiddling their thumbs for some of the expedition, which might be enjoyable, might not be, depends on the person. So yeah, typically between 8 and 12 people would come offshore.
Great. So Ashton Nicholson has asked about a bit more about the combi float type facility that you mentioned, and wondered if there's any scope to modify that design or get something that can also fill the gap between 55 to 90 meters water depth.
Yes, yeah, that's a good question. So the combi float, as far as I understand it, the maximum is 56 meters water depth, and that's only with this leg extension option. I think that the kind of standard combi float, I think, is only 46 meters. So they can extend the legs a bit to get you that little bit of extra water depth. And so I don't think, certainly that particular combi float version of the modular platform wouldn't be able to reach that range of between 55 and 90 meters. I don't know if there are other modular platform manufacturers out there that might. You're probably starting to look at a bigger vessel to cope and to hold those longer legs to get those deeper water depths. So I would think it would be unlikely that you would have that kind of this combi float type modular platform that would get there. I think if you're going to target the 55 to 90 meter range, you're looking at either a lift boat, and then you have to accept the limitations that come with that, or a geotechnical rig, in which case you have to use heave compensated wireline drilling. So there's some trade-offs there in that 55 to 90 meter water depth range.
Okay, thank you. So Damon asked if you could comment perhaps on the new onshore, offshore amphibious expedition initiatives.
Yeah, that's good question, Damon. So IDP is trying to encourage more amphibious, or kind of land to sea transect type proposals, where there's an onshore component and an offshore component. And because of the shallow water depth areas that MSP find themselves, you can see how MSPs would become a natural partner for these land to sea proposals. So some of these very shallow water depth platforms that I've mentioned already, they could be highly suitable for such proposals. So that's definitely worth proponents to think about, is that we now have a system where we're not limited to just land or just sea. If your science requires straddling the coast and to have an offshore component and an onshore component, then there is a mechanism where you can submit a proposal to both ICDP and IODP to have a joint expedition, land to sea expedition scheduled